We've been studying refraction. Refraction is when light changes from one material to another material and bends. It's going to bend if there's a change in speed. And there's some math we have to be able to do with that. The first thing we're going to talk about is called the index of refraction. And the letter for index of refraction we're going to use is going to be n. And it's a measure of speed of light in a material. The equation for it is n equals c over v. C is the speed of light in a vacuum. And v is going to be the speed of light in the material that we're studying. Now, there's a couple things that I want you to notice about this. N for a vacuum is going to be, I would take the speed of light in a vacuum and divide it by the speed of light in a vacuum. These are going to be the same numbers, so I'm going to get 1. For any other material, the fastest it can be is in a vacuum. It's going to be slower, so this number on the bottom is going to be smaller than the number on the top. If I have a fraction where the number on the bottom is smaller, the value of that fraction has to be greater than 1. So n has to be greater than equal to 1. It's 1 for a vacuum and close to 1 for air, and it's going to be greater than that for any other material. Slower materials have a larger n. So the speed is inversely proportional to the n. The slower the speed is, the smaller the bottom of the fraction is going to be, and the greater the value for n is going to be. So slower materials have a larger n. Let's just do a quick mathematical example. Okay, what is the speed of light in a plastic with an index of refraction of 1.5? So we plug into the equation, n equals c over v. I would get 1.5 is 3 times 10 to the 8th over v. And when I solve this, I would end up with v is 2 times 10 to the 8th meters per second. And that's less than in a vacuum where it's 3 times 10 to the 8th, so the answer makes some sort of sense. Now, there's another little equation that you might see sometimes. It's not on the reference tables for AP, but it's kind of useful. So I'm going to write it down. N2 over N1 is lambda 1 over lambda 2 is V1 over V2. Okay, this is called the relative index of refraction. N is the absolute index of refraction, comparing it to the speed of light. But if I wanted to compare two different materials, sometimes this is a little bit easier. And so the n of the second material over the n of the first material is equal to the velocity of the first over the velocity of the second. That makes sense because n is inversely related to speed. So I have to flip these over. So n2 over n1 is v1 over v2. And you'll remember, just above this, we said that in the fast material, the wavelength is bigger. So wavelength and velocity are directly related, and they're inversely related to the n values. Now, what you're mostly going to be doing with this is something called Snell's law. And the equation for it is n1 sine theta 1 equals n2 sine theta 2. So here we have an example. I have light traveling, it's in water, and then it travels through the water, gets to this point, and then it is going to travel into this crown glass. Okay, so let's start to think about this. Eventually we're going to have to calculate these things, but first let's just sketch in the reflected ray and the refracted ray. We've been talking about reflection and refraction separately, but every time light hits a surface, it's going to do both. Some of it's going to reflect, some of it's going to refract. So here's my surface, The light's coming down like this, it's going to hit that surface, and it's going to reflect back up this way. So we can label this reflected. That's the reflected ray. And what we learned about reflection is this angle of incidence is the same as reflected angle. So I know I'm going to label this theta r for the reflected. Theta r is going to be 35 degrees. So reflection is very, very easy. Now, refraction is, we're going to have to calculate the angle using this Snell's law. But let's just think about what it should look like. Okay? I'm going from water with an n of 1.33 and to crown glass with an n of 1.5, so the n is getting bigger. Remember, the n values are inversely related to the speed, so if this is getting bigger, the velocity is getting slower. So I'm going to make a note that this is the slower material, and this up here is the faster material, because the faster is smaller n. And we said when we go from faster to slower, what should happen to the angle? The angle is larger where it's faster. So the angle here is 35 degrees. I know the angle in here is going to be less, so I'm going to just sketch it in. And I know it's going to go down a little bit more like this, and this angle here is going to be less than 35. Now, in this equation, n1, 1 would be the first material. So n for the first material times the sine of the angle in that material equals n2 sine theta 2. So I'm going to label this one theta 1. Label this one down here theta 2. And we have to find that angle. So we're going to use that equation to solve for it. So n1 sine theta 1 equals n2 sine theta 2. n1 is, the n for the water is 1.33. Sine theta 1 is 35. n2 is the n for the second material, so it's 1.5 times the sine of theta 2. And now it becomes simple to solve for theta 2. I would divide by the 1.5 and then take inverse sine. When I do that, I end up with theta 2 is 30.6 degrees. Now we predicted up here, because it's a slower material, theta 2 is going to be less than theta 1, and mathematically it turned out to be less, because theta 1 was 35, theta 2 is only 30.6.